Yes, so just heads up, this lecture will be recorded. I think that's fine. Okay, all right. I suppose we'll begin. Good afternoon, everyone. Thank you for your time, and thank you for coming here, making an appearance. So this is a Newitt Lecture, and it is one of the flagship events of the Chemical Engineering Department at Imperial College London. So Newitt Lecture is really to commemorate the work and dedication of the Professor Dudley Newitt has contributed to the department. So this year, it's the 47th Newitt Lecture, and we have a very special guest joining us today, and it is Florence Gschwend. So just a tiny thing about her. She's a Forbes 30 under 30 nominated in 2017. So I'll give a brief outline of the event. We'll begin with an introduction, introducing how the department, sort of the conception of the department and where we are today. And we'll talk a bit about the namesake of this lecture, Professor Dudley Newitt, and his contributions to the department and even to the wider community. And we'll introduce our speaker, of course. And we will have the main event where Florence will talk about her sort of journey with Lixea, and we'll follow with a Q&A. And finally, to conclude the event, we'll have the SCACAs, which is the Student Contribution and Citizenship Awards, and it is to sort of recognize students who have made an immense contribution to the department. And we'll also recognize recent graduates who have won a prize that has been awarded by the IChemE.
Thank you, Elton. 115 years ago, in the basement of the chemistry department of the Royal College of Science, a couple of innovative thinkers proposed a new addition to what would become the Department of Chemical Engineering as we know it today. This meeting would prove to be faithful to the creation of the department. 4 years later, in 1912, Professor William Bone would become our first head of department, a title passed down to today, held by our dear Omar over here. Very soon after that, the department attracted a lot of attention from all places. Interestingly enough, though, 1912 was an important year for another reason, although a more sinister one. Does anyone here remember what happened on the 15th of April, 1912? Well, more recall, or no? Well, the unfortunate sinking of the Titanic. You might ask, why is this relevant to the Newitt Lecture? Well, Professor Bone actually had canceled last-minute plans on the Titanic because he was asked to come here to become head of department. Talk about fate, you know. History would have been very different if he did get on that boat. In 1922, the Institute of Chemical Engineers was founded, also known as IChemE, with Professor John W. Hinchley and Professor Dudley Maurice Newitt from our own department as founding members. More on Professor Newitt later. In the 30s, taught courses started being offered. The first undergraduate course was offered in 1937. Can you guys guess how many students there were in 1937? 4. We've come a long way. ChemEng-Soc, as you can see, was found in 1935 by students at the recommendation of Professor Hinchley, with Herbert A. Humphrey being the first president. A title also passed down to today, held by our beloved Paulina, who's not here today. ChemEng-Soc held its first annual dinner in 1945, which is a tradition that is still going strong to this day. Fast forward a couple of years, a couple of decades actually. Roderick Hill Building is opened in 1957 to house the ever-growing student intake. For the same reasons, ASEX Building is also opened in 1966 with new lecture theaters and a pilot plant lab area. Some of you might have wondered why it's called ASEX. ASEX stands for Aeronautics and Chemical Engineering Extension. Unfortunately, aeronautics is no longer with us. However, it would be very odd to remove the A, as many of you can imagine. 1980 was the first year where the first 4-year undergraduate course was offered, and in 2012, ABB sponsored a renowned state-of-the-art carbon capture and storage pilot plant. Today, the chemical engineering department is flourishing and houses over 800 students, with intaking over 150 every year. Who knows where our department will be in another 115 years? So, the namesake of this lecture, Professor Dudley Morris Newitt. Born to Dunn and Alice Newitt in 1894 in Putney, he was the eldest son in the family. After 16 years of study, him and his older brother Lewis went to Scotland to work as apprentices in the Noble Explosives Company in 1910. Afterwards, he went to study chemistry at the Royal College of Science just across the road from here. At the outbreak of World War I in 1914, he went on to serve in the military. Bravely, he cut his studies short, and with no time to waste, he hurried back to London and enlisted himself as a private in the 5th Battalion of the East Surrey Regiment. He went on to obtain the rank of company commander and earned a military cross for his service. After the Great War, he resumed his studies, a man of true dedication. His military accomplishments failed to cease here. In World War II, duty called again, and the spirit of a 20-year-old reawakened in the 45-year-old self, and he enlisted yet again. He was appointed Director of Scientific Research for Special Operations Executive, SOE. Incumbent, he was responsible for the design and fabrication of technologies that would go towards ensuring that British spies in the field always had the advantage. Little known fact about Dudley Newitt is that he served as inspiration for Q in the James Bond series. He was knighted in 1946. Of course, his accomplishments weren't only military. He obtained a PhD here at Imperial College London in 1924, after being one of the founding members of IChemE in 22. He presided IChemE from 49 to 50, and he became our head of department in 52, and retired after 9 years of service. Dudley Newitt encompasses what a good person is, what everyone should strive for, a brave soul in the face of not one, but 2 world wars, a curious and forward thinker, a great man. His influence flows through the very walls of this department. His thoughts and actions permeate every room and corner, and his memory lives on right here with us.
Next, I will be introducing a bit of our honorable speaker, Florence. Florence did her undergraduate in Switzerland in University of Basel, and then later on she joined Imperial College to do green chemistry, after which she did a PhD joining in this department. Her research in iron-based liquid biomass was very successful. So she founded Lixea to commercialize her research, and then was selected as Forbes 30 under 30 in the science and healthcare sector in 2017. She's now the co-founder and CTO of Lixea, and the slogan of the company, as it shows here, green solution from green waste turns bio waste into biomass fuels. So let's welcome Florence to give her speech.
Thank you. Thanks for the introduction, and thank you all for coming. So yeah, the next half hour or so I'll be talking about how we make renewable chemicals from wood waste and the chemistry of liquid salts that we use for this. Do I just click or there we go. So yeah, thanks. I think you've heard all of that already. I'm from Switzerland originally, did my bachelor in chemistry at the University of Basel, and then came here to do my master's first in the chemistry department. I came for a year, and 10 years later, I'm still here, as it goes sometimes. Then did my PhD here in the chemical engineering department before spinning out what was first called Crystallix Technologies, but we rebranded a few years ago and are now called Lixea. I also want to acknowledge my co-founders at this point. So Professor Jason Hallett, who sits here, and also Dr. Aggie Brand-Talbot, who's a full-time academic in the chemical engineering department. And not last, sorry, Paul down there in the corner as well, who's also sitting here amongst us. Both Jason and Paul were my PhD supervisors here during my time at the department. And yeah, we're certainly very instrumental in making all of this happen, not last because they came up with a wacky idea for a PhD project in the first instance. And we also had, of course, immense support from the department and the college throughout this journey, and also from Climate Kick, with various instances of funding and summer schools and entrepreneurship programs and so on. So over the next half hour, I'll first be talking a bit about sort of the science behind ionic liquids, and then I'll give you a bit of an overview over what biomass is. Before then talking about our technology, which is called the dendronic process, dendro meaning tree in Greek, and IC for Imperial College. We thought it was very clever. And then a bit how our scale-up journey has been and sort of aspects around the company. And then you'll have plenty of time to ask questions. Just before we start with ionic liquids, just to give you a bit of context, so you can then hopefully remember that during the talk, sort of the dendronic process, what it does is it uses an ionic liquid to separate the main components in what we call lignocellulosic biomass, so that's wood and grasses, etc. Now, the important bit here is that it consists of three main polymers, which are called lignin, hemicellulose, and cellulose. And the ionic liquid allows us to separate those, and then you can turn them into beautiful things. For example, molded fibers for trays or packaging products, or sugar for fermentation, resins or bitumen replacement. And what makes our process really unique is that we can work with a number of different input materials, and that also includes wood that comes out from the construction industry and typically contains heavy metals from preservatives. So we can extract heavy metals and make very clean products from sort of like dirty raw materials. So that's just a bit of context before we dive in. So now over to ionic liquids. Ionic liquids are salts that melt below 100 degrees Celsius. For comparison, table salt or sodium chloride melts at about 800 degrees. The reason for the high melting point of table salt, or indeed most salts that we sort of know, is that they're made of very small ions. So in sodium chloride, you have positively charged sodium cations and negatively charged chloride anions. They're very small, so the charge is on a very small volume, and these cations and anions can stick very close together, and these ionic interactions are very dependent on the distance between the positive and the negative charge. So the fact that they're super close together means that they can make a really strong lattice that needs a lot of thermal energy to melt. Okay, in ionic liquids, so for example, this guy here, we call him MnTF2, melts at -4 degrees Celsius. Like sodium chloride, it's got a positively charged and a negatively charged ion. But unlike sodium chloride, these ions are much bigger, and the charge is much more dispersed over a larger area. So here, I've put a minus here over the N, but it's actually it can be sort of like distributed all over these 7 atoms. And here the cation, the positively charged ion, equally this positive charge can be distributed over a much bigger area. So first of all, the charge density is much lower because you have the same charge but over a much bigger volume. And also these ions are much bigger, so they also can't get as close together. And that results just in much weaker interactions between the positively and the negatively charged ions. And indeed, BIMM NTF2 is liquid at an admittedly relatively warm lab, 27 degrees. But the sodium chloride is very much a solid. And we have here another sort of like cartoonish display of how that might look like. So these are ionic liquids. Now, why do we care? So ionic liquids are often praised as sort of green solvents. So these ionic interactions are weakened to the point that it's liquid, but it's still will never go into the vapor phase. So the interactions are still very much strong enough to always keep the liquid in the liquid state. There is a cup of water here, I assume it's water. Even though it's not boiling, it will eventually evaporate. That will not happen to an ionic liquid. You can leave a vessel open with ionic liquid in it and come back 115 years later. Or if Professor Bone had made an ionic liquid 115 years ago, it would presumably still just be standing here. So because they don't have vapor pressure, they're usually a bit safer to handle, so you're not being exposed to toxic fumes. It also means they're more recyclable. So in a process where you're pumping things around and maybe there is a leak somewhere, like if you have a volatile solvent, there's always risk of it escaping. That's not going to happen with an ionic liquid. And also very interestingly, they have hugely tunable properties. So they're also sometimes called designer solvents. So I've put a selection of anions, which is these negatively charged ions here, the first 2 rows, and then cations, so positively charged ones here at the bottom. So these are 8 times 4 different ionic liquids we could make just with these ions here. And you may see that sometimes I've just written R. R is not a chemical element, that just stands for rest. And that represents loads of different things that you could add there. So for example, alkyl sulfate is just kind of like a general term. It can refer to many things, and similarly here, this R can be loads of different things. So for example, we can imagine it being an ethyl group, ethyl being 2 carbon atoms, or propyl, which is 3 carbon atoms, or we can even put functional groups on it. So for example, these are called thiols, it's a sulfur with a hydrogen, or a hydroxy group. And that kind of adds functionalities. So by making the chains longer, we can make a more hydrophobic ionic liquid that doesn't mix with water, for example. But by reintroducing some polar groups, we can then change the properties again. So really, you can sort of design your ionic liquid to have the properties you want it to have. So then you may ask, why haven't ionic liquids saved the world yet? And the price you pay is literally the price. So they're very expensive. So this ionic liquid, BIMM NTF2, you can buy for about $3,000 the kilogram. So in any application, you have to make it something extremely valuable for it to be worth it. And for biomass applications, people have been sort of advocating this ionic liquid. I think they finally stopped trying to use it, but bulk estimates were that you can make it at about $60 the kilogram. The reason why people wanted to use it is because you can dissolve cellulose in it, and then you can very efficiently make bioethanol. But ethanol costs about 60 cents the kilogram, so 100 times less. So if you want to make bioethanol with a solvent that costs 100 times the price of ethanol, you need to make a lot of ethanol to pay back your solvent, and then you haven't paid for anything else yet. So then you haven't paid for your feedstock or your capital cost or your energy requirement. So yeah, not great. So that's also what Jason thought. So he thought, and I quote his thoughts, if they're tunable, why can't we make them cheap? So that's where we started. We looked at ionic liquids that can be made in very easy synthesis steps from raw materials that are available at industrial scale. We are using mineral acids and amines or imidazoles. The mineral acid we're usually using is sulfuric acid. It's a waste product from the oil and gas industry. And then this top one here is an imidazole. The bottom one is an amine. You just mix the two together. You don't need to input any energy because the reaction is actually very exothermic, and that's your ionic liquid. And here the bottom one is called N,N-dimethyl butyl ammonium hydrogen sulfate. There will be a quiz at the end, so please remember. Is a large scale estimate is that it costs about $1 per kilogram, which is way more in line with sort of bioethanol costs. And it's also thermally stable. What I kind of forgot to mention on the other one is that it actually doesn't really perform very well in terms of stability. But this one does. So thermally stable, so you can actually recycle it really well. So that was ionic liquids. Now moving on to the bioeconomy. There are plenty of examples of the bioeconomy around us already. And there's loads of different things we can use in the bioeconomy, but the general idea is that we use biomass instead of petroleum or other fossil feedstocks to make commodity materials, chemicals, fuels, etc. You can use sugar-containing plants, for example, sugar cane, or here in the UK, sugar beet, widely done in Brazil, where they're producing bioethanol from sugar cane. Then there's oily plants like grapeseed or palm, mainly used to produce biodiesel. And then there are starchy plants like potato and corn. Corn is used on a huge scale in the US to produce bioethanol. But you can also use potato starch, and for example, sometimes you get like these starch-based plastic bags, which then also compost or biodegrade more easily. There are concerns with using sort of like food biomass. One thing sometimes there is concern that it will increase food prices, although that's actually not the worst part. Often it's the fact that you need arable land for it. You might chop down sort of like very biodiverse forest land to grow it. So there is certainly good reason to try and look for alternatives. One alternative is using food waste, and there are various processes for that. For example, some like extraction of valuable molecules from orange peel or lemon peel. And then there's also algae, which can be used, although mostly for sort of like high value small molecules. So not necessarily used at the moment, at least not used on a huge scale. But they are being used for a number of different applications. Slightly more strange application was the surgeon who used human fat from his liposuction patients to power his car, but he then did have to leave for South America because it turned out to be illegal. So yeah, anyway, but in the less controversial space, biorefineries in general are a concept where, similar to an oil refinery, you have an input material that is then separated into different fractions, and the different fractions are then turned into a number of products that can range sort of from very low value products like heat, as in burning stuff, to electricity, which is slightly more valuable, to liquid fuels, materials, then sort of like functional ingredients, as we call them, like glues, adhesives, emulsifiers, etc., to very sort of high-end pharmaceuticals or small molecules that are used in higher value applications. So this is the concept of a biorefinery, and this is basically what we're trying to enable with our dendronic process. But the challenge here we start, is so there is a reason why people are using sugars and from food grade sources, and it's really easy to do. You literally just take the sugar and you ferment it, and then you can distill the ethanol, and there's your biofuel. If you're using starch, you already have to do one more step, and that's a hydrolysis. But it's a very easy hydrolysis. So we all eat starch, or most of us, unless we're on a special diet. And we have enzymes in our saliva that can hydrolyze starch. So you might have chewed on a piece of bread for a long time once, and it kind of becomes very sweet. These kind of enzymes are widely available. They function really well. So you can hydrolyze starch on an industrial scale and then ferment it to ethanol. It becomes much more difficult when you try to do this with wood. Anyone who's tried to chew on a stick of wood before probably has realized that doesn't result in the same as eating a piece of bread. The chemistry is more complex, and we need what is here called this pre-treatment step before we can move on to the hydrolysis. So some molecules to look at. So this is sugar, this is glucose. So this is just one molecule. In starch, we have loads of glucose molecules linked together, which we can then sort of, as I called it, hydrolyze into monomers, into single units. In wood, we have cellulose, which is also a polymer of glucose. And the difference is small but significant, and it's just the orientation of this stick here on where the number 1 is written, that makes all the difference. So in starch, you have sort of kind of like a chain that isn't very linear. It's sort of like kinks every time you have a link, and starch actually forms sort of helix structures that are more easily hydrolyzed. Cellulose forms these very linear polymers of sugar, and these then can align really neatly with each other, and you get a really stable fiber, and that's part of the problem. Now, wood also contains hemicelluloses, which is another polymer made of sugar units, which surround the cellulose, and the real problem is lignin. So this is what the plant produces to protect itself from being eaten all the time or from being degraded, and this is not made from sugars. So these units, these are sort of aromatic subunits that are linked together, and this lignin really protects the wood from sort of falling apart all the time or being hydrolyzed, sort of nature's protection from it being eaten. And this is why we need this pre-treatment step. So really we need to sort of ideally remove the lignin and really make the cellulose available so it can be hydrolyzed. Wood is also referred to as, or is a compound called lignocellulose. Ligno coming from the Latin wood for wood or tree. And the reason why we do want to use it is because it's the most abundant renewable resource on Earth. So it's produced at about 220 billion tons per year. And as I produced, it's literally just growing in the forest, right? It's some of it we purposefully grow, but there's obviously loads of forests that grow without, luckily, without our intervention. And it comes in a lot of different forms and shapes. So it's not just trees or what we would sort of usually think of as wood. It's also sort of the fibrous component in wheat, for example. So when we grow wheat, the straws are made of this lignocellulose. Grasses are mostly made of lignocellulose, and also sugarcane bagasse. So the fibrous residue when you've squeezed out the sugar from sugarcane is lignocellulose. And then there is obviously virgin wood, but there's also a whole lot of waste wood from the construction industry and furniture industry, etc., that is available. And what sort of unites these different types of biomass is the lignocellulose cell wall. So that's the cell wall of the plant. Here in yellow you have these long fibers of cellulose, so loads of these chains that I've shown you. It's surrounded by, here in blue, the hemicelluloses. So those are these other sugars that are a bit more diverse, that kind of amorphously sort of like go around the cellulose, and then it's all held together by lignin, which is the sort of glue in the wood that holds all of these fibrils together. And broadly speaking, we can divide up the lignocellulose world into 3 main groups. So there are softwoods, which are needle trees, hardwoods, which are sort of leafy trees or deciduous trees, and grasses, which also includes straws and sugarcane bagasse. And they differ from each other mainly in sort of the ratio in which you find those 3 components, but also sort of the chemical structure of particularly the lignin and the hemicelluloses. So those are not exactly the same across these 3 different groups, but there's nevertheless sort of part of the same class of lignocellulose. So let's look at what we can make from them. So cellulose is about up to half of the total weight of the lignocellulose at the end of the plant growth. So that changes during the lifetime of the plant, but once it's a fully grown, an adult plant has about 50% cellulose. It's already widely used, of course. We use it every day. It's used to make paper, but also, for example, textile fibers like viscose are made from cellulose. And then it's also used in a lot of other applications, like as an emulsifier. If you ever pay attention to the E numbers on your foods that you eat, it's E460. It's used as a thickener, caking agent. Also, if you swallow any pills, so most of the pill you swallow is actually cellulose. It's also used in paints, etc. So it has a lot of industrial uses. It can also be used in composite materials, and this is where we get to like things where you could potentially replace common petrochemicals. So you can use it, for example, as a fiber reinforcing in plastics to decrease the overall amount of plastic that you need to use. And you can hydrolyze it to sugars, where on the one hand side, you could produce bioethanol from it, but there are also other routes. So for example, we can produce this molecule here is called lactic acid, which you can then polymerize to polylactic acid, which is used for cups, for example, or food packaging. Or it can also be converted into this molecule here, which is called succinic acid. And from succinic acid, you can get to a whole lot of different molecules, which can be used as solvents or different industrial uses. So it's really like a platform chemical that can potentially replace a lot of different molecules currently derived from petroleum. Lignin looks very different. Once it's extracted from the plant, it's this sort of like brown powder. It tends to be formed at the end of the growth of the plant and makes up to a third of the plant mass. In the plant, it's sort of the fire and UV protection and also the protection from microbial attack. And it's also the glue of the plant. So once it's extracted from the wood, you can, for example, use it again for these sort of properties. The structure depends on the plant type. As I've mentioned, sort of the hardwoods, softwoods, and grasses have slightly different lignin structures. And because it's so different, depending on the biomass and other factors, sometimes a bit challenging to do, to find higher value applications, and often it's burnt at the moment. But it could potentially be used in a lot of different applications. One that we're really working on is in resins, so for like furniture products. And other people are trying to break it down into monomers. So this molecule here is called phenol. It's a widely used chemical in the petrochemical industry. And if you look at the polymer here, you can see that if you cut this in the right places, you might very well produce quite a lot of phenol, but it's not that easy to do. Some people are trying to put it into sun cream. So there are a lot of interesting applications being researched at the moment, but not very many yet sort of at industrial scale. But so the natural properties it has lends it very well to be, for example, blended into hard plastics, for example, for fire and UV protection, etc. Then other products that we can produce are from the hemicelluloses. These depend highly on the plant species, but one molecule that is of great interest is called forforol. We can produce this from a sugar called xylose, where And this sort of happens in our process whether we want it or not, so that's very convenient. And we can produce this molecule called furfural. And another molecule that we produce in our process from the hemicellulose is acetic acid. So hemicellulose comes with these acetate side chains, which we can hydrolyze to acetic acid and isolate. Here's just an overview of what you can make from furfural. I mean, I know it's a terrible resolution, but furfural is one of those platform chemicals that really can be turned into loads of different things, which is why we're really interested in it. So now, how do we actually do this? And at this point, I want to acknowledge Aggie, who's sort of come across this invention during her PhD because she forgot to dry the ionic liquid, and then turned out that it works much better if you have some water in the system. So we use biomass from different sources and an ionic liquid, and we put it in a pressure tube, or it's what we used to do, and heat it up. We cook it, and we dissolve everything but the cellulose, which we then filter out, and you can hydrolyze it into sugars. When you collect the liquid, we call it the black liquor because it's black. We collect that contains the lignin now, and we add water, and this is where the lignin precipitates out. And what is key here is that our ionic liquid does not dissolve the cellulose, but it dissolves the lignin up to a certain water content, and if you go above that, the lignin precipitates out. Now, that was sort of the core process. When I did my PhD, I was looking at metal-containing waste. Copper, chromium, and arsenic are typically used wood preservatives, and the idea was to extract those at the same time. And indeed, these metals end up in the ionic liquid, and we can then plate them out again using an electrolysis step, and then recycle the ionic liquid. So that worked wonderfully, and part of the reason why I'm here today. Because it worked so well, we then decided to spin out a company and scale up this process. So we started by doing things in bigger and bigger vessels. Luckily, we had some engineers helping us out, because otherwise, Aggie and I, both trained chemists, would probably have ended up with some very, very large round bottom flasks. But so we started with the pressure tubes. Then we got a 1.5 liter reactor. At this point, running the reaction was one thing, but then you had to filter things. So I went on Amazon and purchased a cider press to run my filtrations. It worked somewhat okay. But then we rented an open access piloting facility where you can see a very exciting Aggie attending our scale-up trials. So you can see the 1,000 liter reactor that we used for our first scale-up tests, and this filter press in the foreground that we use for our filtration, just much better than a cider press, I assure you. And here a very proud Jason with the 200 liters of ionic liquid that we had to produce for it, because of course the ionic liquid is currently not available for purchase from any sort of supplier, so we had to make it ourselves here in the lab. And now we've built our own pilot plant, so that's very exciting. The sort of what the pilot plant does is roughly this. So the engineers in the room can follow me. We don't have a conveyor, but we have a sort of pre-treatment reactor where the cooking is happening. It then gets pumped to a filter. It gets washed in the same piece of equipment. So this filtration pulp wash happens in the same place. The liquid filtrate goes to a lignin precipitation tank where it's diluted, and then again, so the lignin precipitates and is filtered out. Again, this filtration and washing is happening in the same piece of equipment. And here the filtrate goes to a distillation column where we distill out the water that we've added for the lignin precipitation. And at this point, we also distill out the furfural and acetic acid products from the hemicelluloses. And we recycle the ionic liquid, so it goes round and round. So here's some photos of our pilot plant. Here on the left-hand photo, you see a paper mill. It's not our plant. It's a paper mill. We're across the street from the mill in one of the warehouses of the paper company. Here on the middle and the right-hand side picture, you see our pilot plant before we got the insulation done. So now it's not as shiny anymore. But got some vessels, filters, evaporator, a lot of pipes and pumps. So our pilot plant's been operating since May last year. We designed it in-house, so our engineers did the design, and it can process about 20 kilograms of feedstock per batch. We've so far run it on spruce sawdust and sugarcane bagasse, and it's delivering a lot of engineering data for our process models, and also cellulose and lignin, finally, sort of the kilogram scale. So we're also able to send off samples to potential partners and customers for prototyping. So huge milestone. So now the business pitch. So why are we actually doing this? So of course, the aim is to really offer an alternative to the petroleum-based industry. And as I've mentioned, this is not that easy to do. You can use food-grade sugars or food-grade sources, but they're actually quite expensive. And another problem is that the petroleum-based industry is extremely optimized, and they make use of every single drop of oil in a barrel of oil. And often in the bio-based industries, we're not quite there yet. And also the food-grade sources come with some sustainability penalties. So quite often they need fertilizer input, they need arable land, etc. So there is a need for using new resources. And the good news is that there are over 1 billion tons of wasted agricultural residues and also wood waste across the globe every year. The bad news is that they're really not used very well. So a lot of it is burned or landfilled. Burning, of course, leads to a lot of air pollution. So Southeast Asia, for example, where they do crop burning, they have huge public health problems because of the air pollution that it creates. And also in, closer to home now that a lot of people, not so much in the UK, but in Europe, a lot of people have switched to using sort of wood stoves again for heating because the gas is so expensive and you can really smell it in the streets. It's not great for air quality. So potentially a lot of feedstocks available. To give you some numbers, sugarcane bagasse, which is produced from cane sugar production. There are about 150 million tons available every year across the globe. Rice straw, huge in Southeast Asia, but needs to be collected, so it's usually just left in the field, but over 600 million tons. Virgin wood residues and wood waste is about 100 million tons, and also wheat straw, which of course in Europe we grow a lot of as well, is about 1/4 or 250 million tons. So there is a huge potential which is sort of waiting to be unlocked. I've already told you how we're doing it. So now in terms of what we're focusing on is really trying to valorize all those different fractions. I said the petroleum-based industry is extremely optimized, so we're really trying to catch up with them and make use of the entirety of the biomass. We also see the bio-based chemicals and materials markets growing extremely rapidly, but to sort of sustain that growth, they do need the input materials to enable them to produce. So this is where our cellulose, lignin, and small molecules come in. So the sort of key markets we're focusing on at the moment are molded fibers from the cellulose. So like egg trays is the thing that everyone knows, but it's also used in like electronics packaging and a lot of other packaging applications. And then cellulosic sugars, for example, for bioethanol, but also for many other products. So the sort of synthetic biology space is growing extremely rapidly at the moment, and at the moment mostly using food grade sugars. So there is huge potential to replace that. With the lignin, we're focusing a lot on phenolic resins. There's some initial products on the market already. So this like furniture products, for example, where you have like a resin that holds like the plywood together. And also bitumen replacement, which is potentially a very large market. We're also interested in bitumen replacements because it's a market that exists almost anywhere in the world where there's people, because we build roads wherever we are. While the resins market is maybe a bit more specific to where you have resin producers. On the small molecules, the main ones are furfural and acetic acid. Furfural is a specialty chemical, but as I've shown you, it's one of those platform chemicals that can be used in loads of different applications potentially. Acetic acid is a huge commodity chemical already. Kind of sounds bio-derived, but 99% of acetic acid actually comes from petroleum. So there is a huge potential to increase the bio-based acetic acid sort of market share. Used in all sorts of things. I've written down coatings here, but it's used in so many different applications. So our roadmap from here really is, and if someone is looking to invest some money, please let me know. No. So we've now built our pilot plant, and through a grant, mainly from the European Innovation Council, it's been a huge milestone for us. We've been able to really grow our team, so we're now 8 full-time and 5 part-time, mostly based in Sweden, where the pilot plant is. And we're now really looking to sort of accelerate our commercial development. Our next goal in terms of technical development is a demonstration scale project. So we'd be looking at about a 25,000 ton per year plant, so quite sizable. And then from there, we're looking to then scale through licensing agreements. So our vision is really that our technology would be used across the globe by companies that have raw material or that have a specific product in mind and are running the technology. And so that was the lecture. So I think there's time for questions.
Yes. Thank you, Florence. It was a very eventful presentation. So yeah, there's time for Q&A. Are there any questions?
Okay, so I missed out the first part of the presentation. What is lignin mainly used for?
What is lignin used for?
Yeah.
So the honest answer is not much at the moment. So it's mainly produced in paper making, but it's usually just burnt internally in the process for process heat. So they don't really isolate it as a product.
So you say if it's mainly for it's for paper making, paper manufacturing, right?
So it's produced as like a byproduct from paper production. So basically, the paper making process uses wood. Wood contains lignin, but you don't want lignin in your paper. So in the paper making process, they extract the lignin, but they don't actually isolate it. They just burn it directly to generate the heat for their own internal processes.
Okay, so is there like a reason why you guys need to specially filter out lignin and classify it as like a product?
Sorry, can you repeat it?
Because you guys actually have like taking extra steps to actually filter lignin out.
Yeah. So so in the paper making process, it's a very old process. It's been around for about 150 years or so. The problem is that the lignin is mixed with the cooking chemicals, and they need to recover the cooking chemicals. And the easiest way to do that is to burn the lignin, and then you recover the chemicals. There is a process to extract lignin as a product. The problem there is that you still have some of the cooking chemicals in the lignin, and the chemicals are sort of sulfides, which smell of rotten egg. So you get this lignin that has a very unpleasant smell. So that's the main reason why there isn't a huge market for lignin at the moment. In our process, we don't have sulfides, so our lignin actually smells really nice. I wish I'd brought some. It has this like vanilla brandy butter smell. So in our process, we dissolve the lignin and then we precipitate it and filter it out. Our lignin is much purer, it smells much better. So our expectation for sure is that we will be able to develop applications where the existing paper industry has struggled to do so because they've had this problem of this very unpleasant smell, which, as you can imagine, if you put it into a furniture product and your wardrobe keeps giving up this rotten egg smell, it's not a great selling point. And I think a few years ago, someone tried to, or 10, 15, 20 years ago, they put into car bumpers, and that was okay as long as the cars were parked in the street. But once you put it in your garage, you then have very unpleasant smell in your garage. So, so that's the reason why historically no one's really succeeded in making anything from lignin. But in our process, first of all, our lignin comes out whether we want it or not. So we have a huge incentive to do something with it. You can still burn it, but it's a very low value application. So we're really interested, and it's not just us, a lot of companies, including some of the paper producing companies, are very actively looking to make new things from it. Stora Enso, which is a big paper company, they have this Northvolt project now, so they're trying to make electrolyte materials with it for energy storage out of lignin. There is resins, there is bitumen, there is emulsifiers, so there are a lot of applications in the pipeline, just that in this very moment, unfortunately, very few things are made from lignin.
Thank you very much.
Yeah.
Thank you. So first of all, thank you for the lecture and congratulations on the achievements. I would like to ask about the overall energy balance of your process. Is it overall an endothermic or an exothermic process? And especially the water distillation seems to be like an energy intensive step.
Yeah, so yeah, we don't really know if the overall process is exothermic or endothermic, probably close to zero overall. But the energy input for the the reaction pathways, I don't know if they're exo or endothermic, but yeah, you need to have energy input for the distillation. That's our biggest energy cost. We can use sort of a multi-effect evaporator system to do some heat integration there. Should have said I'm not actually an engineer, so I get our engineers to do those calculations. We can, in our models, we usually do rely on an external energy source because we think it's more sensible to sell our products rather than to burn them. But you can be more energy self-sufficient if you burn part of your lignin. We certainly anticipate to burn sort of like the undersized fraction of the feedstock. There's also some wastewater that gets treated into with an anaerobic digestion step into biogas, and then you have a biogas boiler. So there's some level of energy generation within the system, but we in our models we usually work with a locally available energy source. So whatever it may be, yeah.
Thank you. John.
Oh. You're getting your exercise today, John. Thank you for the talk. It was really interesting. And thank you for focusing on the scientific discovery as well, which is a good story. So you ended by saying that the route map goes to exit, which I think means that, I don't know, Elon Musk comes in, buys the company for lots of money.
Hopefully not him, but yes.
Yeah. So does part of you think or hope that Lixea could become, the BP of biorefining in 20 years?
Did you say the BP?
For example?
Yeah, I mean, we certainly think it's a platform technology that can be used in loads of different geographies and for different markets. And yeah, it is a refining process, right? So in that sense, we're certainly looking to not on our own, of course, but to be part of what is going to replace the petroleum-based industry. So yeah, whether or not we're the next or the evolution of BP, yeah, to some extent, I guess that is where we're aiming for. We certainly are not going to do it on our own, so we're producing sort of the equivalent of like the different fractions that come out of an oil cracker, and then we need someone to convert them. So we're not actually developing any resins ourselves. We're working with resin formulators. We're not producing any molded fiber products ourselves. We're working with companies that make molded fibers. So yeah, we're certainly, as part of the sort of growing bioeconomy ecosystem, we're trying to be the the cracker. Yeah.
Okay, I don't know, maybe you mentioned it in the talk or not, but I can't quite remember. Very nice talk as well, thank you very much. So you mentioned for your pilot, you had to essentially make your ionic liquids in the lab because there's not really a market for them right now. So are you going to be generating the ionic liquids in your kind of scaled plants as well, or what is the kind of the plan there? Are you going to be also generating that, and what are the costs and limitations there, and how's that balancing all out?
Yeah, it's a good question. We haven't really come to a conclusive answer ourselves, but the last synthesis step, which is mixing the acid with the amine, is really dead easy. So you could do that on your own site. So when you have your plant, producing the amine requires a bit more sophistication. So there we would probably rely on a local petrochemical, for lack of a better word, it's called chemical company. So, you know, BASF or Dow or anyone in Europe or the US or China can produce amines. So they're produced in any sort of chemically advanced country. We purchased for the pilot test these first pilot plant runs where we used an open access facility. There we produced it here ourselves with a reactor that I think is still on the third floor here. So we just purchased the amine and the acid. For the pilot plant in Sweden, we got it shipped to a site in Austria. So we got a different company to then do the mixing for us because we couldn't get the permission to do it in Sweden because the amine is flammable. There we got like a toll manufacturer to make it for us. But yeah, in the long term or for sort of like demonstration or commercial scale plants, you'd probably get a local chemical company to make the amine at scale and then either make the ionic liquid also, or then ship the amine together with the acid to the site of your plant and make it there.
I have actually two questions, one to your process and one more a little strategic. So regarding your process, what is the degree of recycling of the ionic liquid? So how much do you recover?
So it's a good question. The good news is that we don't detect any degradation product from the ionic liquid. So the place where the ionic liquid leaves the system is through incomplete washing of the products. Our pilot plant doesn't wash very well, I have to say. But the paper industry, which also does chemical recovery through washing, recovers about 99% of its cooking chemicals. And because in what we're doing is not that different from what the paper pulping process does, we would anticipate that we can also recover 99% of the ionic liquid. So we would lose 1% to the cellulose and lignin product.
But it stays in your product.
Yeah, so you basically just have like a small tiny contamination of your product. Yeah.
Okay. The other thing was more, as I said, strategic. When you think about the whole energy generation, now moving more towards renewables. So ultimately, we hope to get away from fossil fuels. Do you see that rather as an advantage or a challenge for your process?
So in some ways, we do compete with biomass to energy. So that we see as a potential challenge because that increases our feedstock prices, because you then often also have subsidies for sort of like bioenergy generation. But in general, the move to renewables or energy security, etc., is of course good for us. So that looking at producing more domestically, importing less, especially for countries like Sweden or Finland, which have huge amounts of forest resources. So overall, I think the development is good. What is the big challenge potentially for us if there's big subsidies for using biomass for heat and energy, but not using biomass for other products, because that sort of then is not a level playing field, right? And we need to pay an artificially inflated price for our feedstock.
Hey, Florence.
Hi.
Within the bounds of reason and sanity, what do you think the most useful thing that Imperial could have done to have made the process of spinning out the company easier? You've only got half an hour.
I'll get back to you on that one. No, I mean, so a big challenge been sort of the equity stake that was taken from the company. That's kind of never made conversations with investors easy. And the other thing that we're now seeing is that as we're talking to investors who are then thinking ahead about an exit, is if you're selling the company, okay, so there are 3 patent families surrounding this technology. They are owned by Imperial College, and they're exclusively licensed to Lixea with the right to sub-license it. So far, so good. But the problem is, once you get to the point where a company says, yes, we want to buy your company, they would want to own the IP as well. So there needs to be sort of a clear route to acquiring the patent, not just the license, which we have, but the ownership of the patents. There needs to be a clear route to that. If it comes with a price, or I mean, it will come with a price tag, of course, but there needs to be a clear route that can be sort of anticipated and executed in a timely manner, because that leaves us at the moment in quite a high level of uncertainty, which might put some investors off if they don't know that there will be a route to exit. Yeah.
Thank you. Any more questions?
Not particularly. To be honest, it's been difficult, and if someone can do this much faster than we do, then they probably deserve it. But yeah, there is. So and well, to some extent, if someone does try to copy it, it means you're doing it right. So you've done something right. So yeah. Not super concerned. We have the patents. We have a lot of internal know-how. Yeah. So there is a company in Canada called Crystalix Venture Capital. And you might think they have nothing to do with what we're doing, and we thought so too, but their lawyers sent us a cease and desist letter, and we replied, well, we don't really think you have grounds for it, but if you pay for our rebrand, we'll do it. And they were like, thank you very much, but no, we won't pay, and please still cease, desist, or whatever it's called. So we rebranded because we thought that was cheaper than a legal battle, even if we were to win it. And also it got misspelled all the time. It was very difficult. Crystalix, people didn't know how to pronounce it. So kept the last 3 letters, Lix, and then we added Ea or Ea. So that's also Ea. It means good in like Estonian. I'm not going to tell you why Estonian, but so it's kind of like liquid good, or the good liquid. Yeah. We checked trademark stuff. We checked URLs. I'm not going to make the same mistake twice. But yeah, really often emails didn't arrive because people misspelled Crystalix. It was, and then we weren't just Crystalix, we were Crystalix Technologies. It was really long. So now we're just Lixea. So I did a lot of sort of entrepreneurship programs during my PhD. And yeah, but I mean, just start. I don't know. Yeah, I mean, every day was a challenge.
Oh yeah.
How did it feel like when you found out that you were nominated or your name was earlier in the 30s? Because there's not a lot of that per year.
Yeah, to be honest, it came at a time where we were so in the early stages that it felt a bit undeserved at that time. I mean, we hadn't even incorporated a company yet, so it was, yeah. Now I feel worthy, but at the time it was a bit like, yeah, I don't know. But maybe they knew something. I don't know. Yeah.
Can I ask a question as well? Where do you think your future market is if you were to like scale up the company and the production?
I mean, you know, loads of different markets, I guess. So, so very generally speaking, in the chemical process licensing market. But yeah, I mean, we have conversations, for example, with a company that runs sugar mills in South Africa, who has sugarcane bagasse. We're talking to American advanced biofuel producer, producer of meat alternatives, paper companies that want sources of sort of non-wood pulp because deforestation is a big topic, so they want other raw materials. So yeah, geographically and also in terms of industry is very diverse. Yeah.
Thank you.
So since ionic liquids are
I mean, not me, but Jason's got like an army of spin-out companies that does that. So there is one that looks at extracting dyes from textiles, metals from slags from foundry industry, vanadium from tarzans, you name it. Jason's probably doing it. Waste electronics. That's my next one.
Are you happy doing this one?
Ask again later. It comes with its ups and downs. Yeah, some days are better than others. But certainly going on site and seeing your pilot plant, that's a good day. That's a good day. I think I'd say there's loads of routes, and maybe I'd also say think about why you want to do it. Sometimes I talk to people and they're like, they think it's like extremely glamorous, and it's really not. And there's, I think, sort of understanding what it is that you want to achieve, because one thing that I sometimes think about is now I've spent almost 6 years on this and it could still fall apart within, nothing. And then what have I done? Then I've spent 6 years on this and not really achieved anything. We haven't saved any CO2 so far. If anything, we've produced more, right? So if you're actually interested in making an impact, there might be other routes to do that. So it's not for everyone. It's not an easy journey. Don't want to put anyone off, but yeah, it's not as glamorous as it looks, and it might all be in vain. Sorry. Yeah.
Do you still have any summer internship positions?
Yeah, all the time, particularly in Sweden, but yeah, potentially.
I sent you my CV tonight.
Yeah.
Thank you. Yeah, if we don't have any more questions, we shall proceed to the next part. Thank you very much.
Right. So, as said in the outline, we'll now move on to the student awards. First, we'll present the Student Contribution and Citizenship Awards, SCACAs. So, would the head of department, Professor Omar, please come up and present the awards? Right. So we have 4 students who have been highly commended and noted for their contribution to the department. Count.
So the first student that's highly commended is Peter Chen. Is Peter here? Yeah. Come take a photo. You want to come? Yeah, I think you better come. Yeah. You wanted to stand there, sorry. Yeah. All right, next. That's meant to be a surprise, or no?
Well, I mean, you're going to say.
All right, okay. So the yes, can we call Jonathan down here as well? Well done, Jonathan. Right, so the next one is Marique. Highly commended. We thought you weren't going to be here, Marique, so I was going to do this in absentia, but I'm glad to have you with us today. Come over here.
Thank you very much.
Right. Over there. Right, thank you very much. Right, next one is Karen Ying. Is Karen here? Next one.
You want to take a photo?
Oh, photo, yeah.
Highly commended one.
Yeah. Right. So what they go back and sit down, or you want to stay here?
Well done, guys. Good. Thank you for your contribution to the department. And now, on to the winners for the SCACAs.
Right. Our first winner is Alice Zhu. Our next awardee is Just David, apparently. Right, our next awardee is Nicholas Gerard. And then our final awardee is Brent. I can do another photo.
Yeah.
Congratulations, guys. You must have made an immense contribution to the department. Yeah, the nomination, it was quite tough this year, you know, there were lots of nominees. Thank you, guys. As we said, we're now going to recognize the McNabb Lacey Prize winners, which is an award given by the IChemE.
Yes, it is.
And we'll have Professor Paul Fennell present the certificates.
Right. Thank you very much. And let me, yeah. So this is an award that's given out on an annual basis by the IChemE for the IChemE Best Student Design Project for in terms of sustainability. And Imperial does in general very well. And I'm very pleased. I don't think we need to go through everyone individually. All of you guys come down. And this year, this was Metastic, who did an extremely difficult project. I can, right. Who wants to actually give them out? Yeah, come on, you arrange. It's been a year. Who did an extremely difficult project, looking at the development of new types of artificial meat. So what meat did you end up producing? Was it hamburger in the end? Burgers, and it was just normal burgers.
With onion, was it?
Ah, yeah. Burgers with onion. But one of the key things for the design project at Imperial, and one of the things that sets us apart, and one of the reasons why the IChemE has asked me to, or has done the highly commended, is because Imperial's design project really does start out with some very basic briefs, sort of saying, go away and make me some artificial meat. Basically it, yes. And after a great deal of blood, sweat, tears, crying, and visits to faith, they've come up with something that was absolutely excellent and was recognised as such by the IChemE. So I commend them, and thank you very much.
Can we have a photograph, please? Would you like to stand next to them? Yeah.
I'll do it. Let me. Here we go. You know.
Excellent.
Can't hold this that long. Cheers.
Well, oh yes, of course.
Right. Who said yes for? Not a discussion.
Okay. Right.
I don't want to drown you in thanks, but I want to make sure that Elton and Zong and John get the appreciation that they deserve for organising all of this whilst trying to do process design projects and attend lectures. And honestly, I don't know how you do it. Well, maybe you don't know either. You've got some catching up to do tomorrow. But everyone, please say your thanks to these three guys here.
All right. Thank you, everyone, for making your time to sort of come to the 47th Newitt Lecture. We really appreciate you making an appearance. And thank you very much. Hope you have a very eventful rest of the evening. It's fine. Yes. What?
We would like to, at the end, give special thanks to 6 very special people to this event. And they are Professor Newitt and Miss Newitt.
Florence and your +1 guest, and of course Omar, Faith, and Colin for really sort of helping us out throughout this whole time. If you could sort of come on up, we have some special gifts for you. Yeah. Thank you.